disease processes either cause or are caused by abnormalities of blood flow. So it's important to have a good grasp of the laws that govern the flow of fluids through tubes. The way a fluid, like blood, flows through a tube, like a blood vessel, is governed by the relationship between the driving pressure of the fluid, its physical characteristics, and its interaction with the walls of the vessel. Pressure is a force exerted over a specific area. By pressing my finger down onto this piece of paper, I am exerting a pressure on the area that my finger covers. Similarly, by pressing on the plunger of this closed syringe full of air, we are generating a pressure within the syringe that is equal to the force with which I am pressing the plunger in newtons divided by the cross-sectional area of the syringe barrel in meters or centimeters squared. A force of 1 newton exerted over an area of 1 meter squared is equal to 1 Pascal, the standard international unit of pressure. The science on this is quite old. The French physicist and physiologist Jean Poisson formulated an equation in 1846 relating the rate of flow of a fluid through a tube to the driving pressure, the length and diameter of the tube, and the fluid's viscosity, its thickness or stickiness. The German civil engineer Gotthelf Hagen independently made similar observations at about the same time, and their work was combined to form what we now call the Haagen-Poiseiulle equation, which states that the rate of flow, Q, of a fluid through a tube with a circular cross-section of radius r is equal to the driving pressure, delta P, multiplied by pi, multiplied by the 4th power of the radius of the tube, divided by a constant, 8, multiplied by the viscosity of the fluid, given the symbol eta, multiplied by the length of the tube. So, the rate of flow, Q, is directly proportional to everything on top of the right-hand side of the equation, the driving pressure and the 4th power of the radius of the tube, but inversely proportional to everything on the bottom of the equation, the fluid's viscosity and the length of the tube. Let's go through the elements of the equation in turn. Flow rate is measured in units of volume per unit of time and is given the symbol Q. So, for example, if the heart pumps out 60 milliliters of blood every second, the flow rate out of the heart is 3.6 liters per minute, 60 milliliters per second, multiplied by 60 seconds per minute. This is also known as the cardiac output. Let me take a bit of a sidestep here. Flow rate is not the same as flow velocity. Velocity is the speed at which the blood is moving within the vessel and is measured in units of distance per unit of time, usually centimeters per second in the circulatory system. That is a distinction that is going to be very important, as we will see. Obviously, the flow rate and flow velocity are closely related. All else being equal, a greater flow rate will necessitate a greater flow velocity, but it's not a simple linear relationship. Why am I mentioning velocity when it isn't part of the equation? Well, because it's a bit like the elephant in the room of the Haagen-Poiseiulle equation. It can completely change the rules that govern blood flow, as we will see in a minute. A fluid will flow along a tube only if the fluid pressure is higher at one end than the other. The greater the pressure difference, the greater the rate of flow. So all else being equal, the rate of flow is directly proportional to the pressure difference, up to a certain maximum rate, which, again, we'll talk about later. In the circulatory system, the driving force for flow is the blood pressure generated by the ventricles when they eject blood into the aorta and pulmonary arteries. The pressure difference is equal to the pressure in the aorta for the systemic circulation, or the pulmonary arteries for the pulmonary circulation, minus the pressure in the atrium of the opposite side of the heart, the right atrium for the systemic and the left atrium for the pulmonary circulation. So, the rate of flow is directly proportional to the driving pressure, but it is also directly proportional to the diameter or radius of the vessel, or rather, to the 4th power of its radius. So, while an increase in the driving pressure will lead to a linear increase in the flow rate, an increase in the radius of the vessel will lead to an exponential increase in the flow rate. Let's go back to the syringes to illustrate this. Here, both of my colleagues have identical syringes, and they are both pressing as hard as they can on the plungers, so they should now be generating a similar driving pressure. However, One of the syringes is connected to a very small cannula with a small internal diameter. The other is connected to a larger cannula, which has a much bigger internal diameter. As you can see, the syringe connected to the larger cannula empties much more rapidly than the one connected to the smaller cannula. To take this to extremes, the syringe in this video is attached to the smallest and narrowest needle we could find. You can see how severely reduced the flow rate is compared with the cannulae. This is because the reduction in flow is raised to the fourth power of the decrease in vessel diameter. Very small decreases in vessel radius translate into a huge reduction in the rate of flow. If you halve the radius of the tube, the flow rate is reduced by a factor of 16, 2 to the power of 4. So, the parameters on the top of the equation are directly proportional to blood flow. What about the parameters on the bottom of the equation, the factors that are inversely proportional to flow? Well, the first is the length of the tube through which flow is occurring. The longer the tube, the slower the rate of flow through it, because the friction between the vessel wall and the fluid is necessarily greater. However, in the circulatory system, the length of the tube doesn't really vary. The distance blood has to travel in order to get from the left ventricle to the right atrium, and vice versa for the pulmonary circulation, is pretty much fixed by our biology. There aren't any shortcuts. However, changes in the length of the tube might be of importance in other circumstances. For example, if you're trying to get fluid into a patient's bloodstream as quickly as possible. An intravenous cannula is a thin tube that is inserted into a blood vessel. Peripheral intravenous cannulae are short, usually 3 or 4 centimeters. They are designed to perforate the skin and enter a superficial vein almost immediately. As a result, it's possible to get fluids through them and into the bloodstream very quickly if you need to. For example, if you are resuscitating a patient who is severely dehydrated or has lost a lot of blood. Central venous catheters are a different matter. Because they are inserted through the skin and subcutaneous tissues into a deep central vein, usually the internal jugular, femoral, or subclavian veins, they need to be longer, usually 10 to 15 centimeters. That means that fluids will flow through them much more slowly. If you find yourself trying to resuscitate a patient who's bleeding to death in front of you, and if you have the choice, use a peripheral rather than a central venous cannula. The second factor that restricts the flow of blood is its viscosity, its thickness or stickiness. The scientific definition of viscosity is a little technical. It relates to the shear stress, the force that a moving liquid exerts on a surface over which it flows. We will look at it in more detail in another tutorial, but in simple terms, a more viscous fluid has a stronger interaction with the walls of the vessel and thus is more difficult to get to flow than a less viscous fluid. Blood is a complex fluid. It is a suspension of cells and plasma, and its apparent viscosity is not constant in all areas of the circulatory system. This makes the science of blood flow, known as rheology, quite complicated. Additionally, changes in blood viscosity can occur in a number of disease processes, and some of these might have an appreciable effect on our patients. The most important factor that influences blood viscosity is its cellular content. By far, the largest cellular component of blood, by volume, is the red cell mass. It is normal for the red cell volume to make up about half of the total blood volume. This is known as the hematocrit and is expressed as a percentage or a fraction. If the volume of red cells is depleted, either by blood loss or by inadequate red cell production, the viscosity of the blood will decrease and blood flow rate might actually improve, although at the cost of a lower oxygen content. Conversely, there is a condition in which the red cell mass is abnormally high. This is called polycythemia and is due to overproduction of red cells. Patients with polycythemia are prone to too sluggish flow of blood through the venous side of the circulation, and when blood moves too slowly, it is at risk of forming clots inside veins, which can have disastrous consequences. Polycythemia is almost unique in that it is effectively treated by a therapy from the pre-scientific age of medicine, bloodletting. A set volume of blood is removed from a peripheral vein, leading to a decrease in the total circulating volume. The body compensates for the loss of circulating volume by retaining salt and water in the kidneys, and over a period of a few hours, brings the blood volume back up to its normal level. However, the total red cell mass has been depleted, so as the blood volume increases with retained fluid, it dilutes the red cell mass or hematocrit down towards more normal concentrations. Temperature can also have an appreciable effect on the blood's viscosity. Fluids tend to be less viscous at higher temperatures and more viscous at lower temperatures. Within the normal range of body temperatures, 36.1 to 37.4 degrees, the effect of temperature on blood viscosity is negligible. However, we occasionally have to look after people who are profoundly hypothermic, low body temperature. For example, people who survive near drowning or who collapse in an unheated environment and are not discovered for some time. We occasionally have to treat patients with body temperatures below 30 degrees. A 5-degree drop in body temperature can increase the blood viscosity by about 10%, which might have a significant impact on blood flow. Another implication of this temperature effect on blood viscosity is seen in blood transfusions, especially when there has been a massive blood loss, hemorrhage. Donor red blood cells are chilled to about 4 degrees for storage. If a massive blood transfusion is needed very quickly, we would try to use a rapid infuser device that warms the transfused blood to body temperature as it is infused, both in order to improve the flow rate of the transfusion and to avoid causing hypothermia in the patient. Blood flowing through a blood vessel doesn't all move at the same speed. Flow is fastest at the center of the vessel and slowest near to the vessel wall, due to friction between the vessel walls and the blood. Under normal conditions, blood flows in a series of concentric, ring-shaped layers that do not mix very much with each other, and the rate of flow is directly proportional to the driving pressure. This is known as laminar flow. However, if the flow velocity is greatly increased, eddies and swirls can form within the vessel, and the pattern of flow transitions from laminar to turbulent flow. Turbulence increases drag, or resistance to flow, such that the flow rate of a turbulent flow is proportional not to its driving pressure, but to the square root of the driving pressure. The likelihood of blood flow becoming turbulent is dependent on the relationship between its mean velocity, density, and viscosity, as well as the diameter of the vessel it is flowing through. This is expressed as the Reynolds number, a dimensionless value that is equal to the fluid density multiplied by its velocity and the vessel diameter divided by the dynamic viscosity of the fluid. If the Reynolds number is less than 2000, flow will be laminar. If it is greater than 4000, flow will be turbulent. At values between 2000 and 4000, the flow might transition between the two. This phenomenon breaks the rules that were established by Haagen and Poiseiulle, and it is important for several reasons. Arterial disease is characterized by the buildup of fatty plaques in arterial walls. These tend to create localized narrowings in the diameter of the vessel, and instead of behaving as a tube, the vessel behaves as an orifice, a short narrow segment followed by a rapid widening of the vessel. When the vessel becomes partly obstructed, the flow rate through the narrowed part decreases, but the velocity of blood flow increases dramatically. This might cause the Reynolds number to rise to a point at which it transitions from laminar to turbulent flow, which will further decrease the rate of flow past the obstruction and might lead to inadequate blood flow to ischemia or hypoperfusion of the downstream tissues. Turbulent flow through larger vessels creates vibrations that can sometimes be felt at the body surface, known as a thrill, or heard with a stethoscope, known as a murmur or a bruit. These signs can be useful for diagnosing critical narrowings of blood vessels or heart valves, and they also form the basis of most of the ways in which we actually measure the blood pressure. The final parameter that we need to get our heads around is vascular resistance. Again, it doesn't fit into the Haagen-Poiseiulle equation, but it's nevertheless incredibly important. Resistance is the force exerted by the interaction between the blood and the walls of the vascular tree. It is caused by friction or drag between the molecules of the blood and the vessel walls, and it opposes the forward flow of blood. The systemic vascular resistance, or total peripheral resistance as it is sometimes called, is the total resistive force opposing forward blood flow throughout the entire systemic vascular tree, the sum of the friction between the blood and the walls of all the vessels it travels through on its way from left ventricle to right atrium. I found vascular resistance is a more difficult concept to get my head around than the other parameters we've looked at. It might be helpful to think of it as analogous to Ohm's law of electrical resistance, which you might vaguely recall from the distant past. Ohm's law states that the electrical potential difference, the voltage, between the two ends of an electrical circuit is equal to the current flow, in amperes, multiplied by the inherent resistance of the circuit to the flow of current, measured in ohms. The amount of electrical resistance might vary depending on how conductive the material of the circuitry are, or how hot it is, for example. So, to recap, the laws that govern flow of a fluid, like blood, through a tube, like an artery, are vital core knowledge for doctors because many disease processes cause, or are caused by, limitations to blood flow through our blood vessels. The Haagen-Poiseiulle equation states that fluid flow, volume over time, is equal to the driving pressure, the pressure difference between the high pressure end of the tube and the low pressure end, multiplied by pi, for a cylindrical tube, multiplied by the fourth power of the radius of the tube, divided by a constant, 8, multiplied by the viscosity of the fluid and the length of the tube. Blood viscosity is a measure of its thickness or stickiness. The more viscous the blood, the lower the rate of flow. Disease processes can change the blood viscosity. The most important of these is a change in the red cell mass, the hematocrit, for example due to blood loss or polycythemia, overproduction of red cells. In the circulatory system, the pressure gradient is created by the heart pumping blood forward into the high pressure end of the tube, the aorta or pulmonary arteries. The driving pressure is directly proportional to forward flow, and the relationship is linear. The radius of the vessel is also directly proportional to forward flow. The wider the vessel, the greater the rate of flow. But this relationship is exponential. Blood flow is proportional, not to the radius of the vessel, but to the fourth power of its radius. Tiny changes in vessel diameter can cause huge changes in blood flow. Vascular resistance is the total force opposing blood flow through a tube, and is therefore inversely proportional to the rate of blood flow. Vascular resistance is directly proportional to the viscosity of the fluid and to the length of the tube. The more viscous the fluid and the longer the tube, the greater the resistance to flow and the smaller the rate of flow. It is also inversely proportional to the fourth power of the radius of the tube, and so very small changes in vessel diameter result in large changes in vascular resistance. Blood flow is normally laminar. The blood doesn't flow at a uniform rate, but instead behaves as if it is made up of a series of concentric cylindrical layers that do not mix very much. Blood flow is slowest at the perimeter of the vessel and fastest at its center. However, if the mean velocity of the blood flow increases, or if the vessel diameter suddenly increases, the blood flow may become turbulent. Swirls and eddies form within the stream of blood. In this case, the rate of flow ceases to be proportional to the driving pressure and instead becomes proportional to the square root of the driving pressure. This can cause limitations to blood flow past the narrowing of the vessel. Turbulence also creates vibrations which can be felt or heard at the body surface. The likelihood of flow transitioning from laminar to turbulent is expressed by the Reynolds number, which relates the blood viscosity and density to the diameter of the vessel and its flow velocity. Okay, one last thing before we finish. If you feel that you've got your head around the concepts that we've covered in this tutorial, please move on to work through the self-assessment SBA exercise. However, in order to get a perfect score in it, you will need to memorize some of the detail. Why not work through an exercise with me now that I guarantee will get the details into your head and take no more than an extra 5 minutes. Let's start with the vocabulary. Here is the vocab list for this tutorial. Go through it until you get everything correct. Poiseuille's law. Q is equal to pi multiplied by r to the power of 4 over 8 multiplied by eta multiplied by L, where Q is flow, eta is fluid viscosity, and L is the length of the tube. Write it down once, cover it, and repeat the equation and the meaning of the terms 5 times. Next, the Reynolds number. Re is equal to rho multiplied by epsilon multiplied by L over mu, where rho is the density of the fluid, epsilon is its flow velocity, and L is the diameter, not the length, of the tube, and mu is the dynamic viscosity of the fluid. Technically not exactly the same as eta from the Poisson equation. If Re is less than 2000, flow is laminar. If it's 4000, flow is turbulent, and at Re is equal to 2000 to 4000, flow might transition between the two. In laminar conditions, flow is proportional to the driving pressure. In turbulent conditions, it is proportional to the square root of the driving pressure.